This presentation is to accompany the Otto Cycle presentation that's on Moodle. So go ahead and open that, and you can listen to the audio. I made a video because later on I might demonstrate a thing or two on the whiteboard. So first slide just shows some of the terminology associated with reciprocating engines, Otto or diesel cycle. Here you see over on the left, top dead center and bottom dead center. So those correspond to the smallest and largest volumes inside the piston cylinder device. Clearance volume, that's the volume when the piston is at the top dead center position. You see the crank mechanisms and then inlet and outlet valves. If you go to the second slide, you see the actual Otto cycle process. So you've got air or a fuel and air mixture brought into the cylinder. As the piston moves down, the intake valve is open. You get to the end of the intake stroke, so now we're at bottom dead center. Compression begins, so both valves are closed. The fuel air mixture is compressed. Somewhere near top dead center, spark fires. Flame front moves through the cylinder very quickly. And then you get the power stroke. So now the piston moves back from top dead center toward bottom dead center due to the high pressure and high temperature. Does work, drives the crankshaft. Then when we get to the end of the power stroke, the exhaust valve opens. Piston moves up, pushes the products of combustion out of the cylinder, and then start over. So then the exhaust valve will close, intake valve will open, draw in more fuel and air. So you can see we went through 2 revolutions of the crankshaft where we got work out during one of those steps. Otto cycle, we're going to model this, sort of simulate this, because there's a lot of complex things going on. So one of the, you'll find the air standard assumptions in chapter 9. One of those is we're going to replace the working fluid, which is either fuel air mixture or the products of combustion. We're going to simulate that as just being air, give it the properties of air. So that's the first step, is compression. Compress that air. Now instead of having that chemical energy change into sensible energy, we're going to simulate that reaction as heat input from an external source. So we have heat in, the second step in the Otto cycle, and we do that at constant volume. That's to replicate the nearly constant volume heat addition from the actual Otto cycle. Now we get power out, the expansion process, and the assumption during expansion and compression is that it's perfectly reversible and adiabatic, so that means it's isentropic, no friction, all those kinds of things. And then the final step in the ideal Otto cycle is kind of an odd one. It doesn't really correlate to any of the actual processes of the actual Otto cycle, but we have to get back to complete the cycle, get back to the initial state. And in order to do that, we have to reject heat. So we model it as a constant volume heat rejection that gets us back to the initial state. If you go to slide 3, you can see the actual Otto cycle on a PV diagram. So if you start with, let's see, the intake valve opens, or exhaust valve closes, same spot. So we have intake, we're at constant pressure as long as one of those valves is open. So the intake valve is open. We go through intake, the very bottom line. Now the intake valve closes and the volume starts decreasing again, so the pressure goes up. At some point, you see the little X there where combustion's initiated, so the spark fires. Pressure increases very quickly. It's not exactly constant pressure, but more or less constant pressure. Then the reaction finishes and the pressure falls as the volume gets up. We get power out. Then the exhaust valve opens. The pressure quickly goes to atmospheric pressure, and we push the products of combustion back out to end up at the other X, there again at top dead center. The standard cycle, We can plot it on PV or TS diagrams on slide 4. So you see the isentropic compression, constant volume heat addition, isentropic expansion, constant volume heat rejection. One parameter that's used to characterize Otto cycle engines is the compression ratio, and that's the volume at bottom dead center to the volume at top dead center. The next few slides have some energy balance equations on them. We'll derive them later on, but essentially we have 3 tools for analyzing either Otto or diesel cycle problems. I'll write these on the board here if I can get this pointed right. So one of these is ideal gas. We're dealing with this as a closed system at all times. So the quantity mass times R is always constant, so we can have P1 V1 over T1, P2 V2 over T2. It's also P3 V3 over T3. Alright, so this is true. We can use that to get around the cycle. Another thing that we can use is isentropic case. So this is for process 1 to 2 or 3 to 4. Isentropic compression or isentropic expansion. And now we have 2 choices. If we're going to assume that specific heat is a constant, so we have constant specific heat, ideal gas, isentropic process, we can write, there's a whole set of equations there on your entropy formula sheet. One would be something like this. I think this one's K minus 1 over K maybe. If we do variable specific heat, we would use this equation. Where VR is only a function of temperature. So, for example, if we were interested in the temperature after compression, we could either solve for VR2 and use table A17 to get us temperature 2, or we could solve this equation for temperature. Here we've made the assumption that specific heat doesn't change along the process, this process anyway, in this case 1 to 2, where it's pretty big temperature range, and so this would be more accurate, where this is actual data that we're using. And then our third tool is energy balance. For example, we could apply energy balance to the process, say 2 to 3. From 2 to 3, it's constant volume heat addition. So I could just model it as a rigid tank I'm putting heat into. This is process 2 to 3. So I could say energy balance for that is Qn. That's the only thing crossing the boundary, equals the change in energy of the system, which would be U3 minus U2.